Good morning, friends. Today I'll be discussing about cyclic redundancy check (CRC) error checking codes. I am Sandeep Kumar, Associate Professor in the Department of Computer Science and Engineering, Cambridge Institute of Technology, Bengaluru. So, what is CRC? It is cyclic redundancy check. It is a powerful error detection techniques which are widely used in data communication. Like LANs, WANs, they are also used in some storage devices to check the errors in the stored bits. This CRC is based on modulo 2 division. In that, we have addition and subtraction, both are same, and they are performed using XOR operation. As we can see here, the addition and subtraction both are same. This is addition and 1 plus 1 is 0, 1 plus 0 is 1, 0 plus 1 is 0, 0 plus 0, 0, 0. So similarly the subtraction, 1 minus 1 is 0, 1 minus 0 is 1, 0 minus 1 is 1, 0 minus 0 is 0. So this is basically an XOR operation. So you can see both addition and subtraction are same here. Here we will first consider the sender side. This is the sender side. The encoder will do this job, and at the receiver side we have decoder. At the sender side we have a data word, k bit data word which is taken. Here k is 4, and using that an n bit code word will be formed here. So n bit code word which is decided, pre-decided. So how you form n bit code word? So you take k bits data word, and there are some number of bits are added as redundant bits here. How they are added? This is basically the remainder of the generator. Here generator is basically a modulo 2 divider. Modulo 2 divider. So this generator will divide the augmented data word. Augmented data word. Here, augmented data word. What is augmented data word? It takes the k-bit data word and it will add some number of zeros here. What is that some number of zeros? So here in our example, 3 bits are added. 3 bits are added to the data word to form an augmented data word. So how these 3 bits are added? It is 1 bit less than the number of bits which are present in the divisor which is used. So now you may ask how the divisor is chosen. So divider is chosen based upon the protocol. It is predefined and agreed upon by both sender and receiver, depending on the protocol which is used in the data link layer. In this example, there is a 4-bit divisor. So therefore, 1 less than that. So 3 zeros are appended. So remember here, how do you form the augmented data word? So augmented data word is formed like data word is taken as it is, and 1 less than the number of bits which are present in divisor are added here. So there are 3 bits are added, or the number of zeros to be added is 1 less than the number of bits which are present in divisor. So now the generator will perform modulo 2 division and it will generate a remainder. Again, how many bits of remainder? It is again the 1 less than the number of bits which are present in the divisor. Or in other words, the number of bits in the remainder is equal to the number of zeros which are appended. So finally, we form a code word. So that is k-bit data word plus the remainder here. Together they are added to form the code word. The code word is sent to the receiver. Receiver now will receive the code word with error or without error. There are two possibilities here. So here you see here the checker will do the same job as the generator. Checker will perform the same operation as the generator, but one small change: instead of augmented data word, it performs the division operation for the received code word. N bit received code word. So the output of the checker is a 3-bit syndrome, that is the remainder, 3-bit remainder here in our example, or the remainder here is n minus k bits is a remainder. And checker will use the same divisor here, which is used by the generator. You can see in the diagram. So same divisor is used by both generator and checker. So the output of the checker is a syndrome. Now the syndrome is the input for the decision logic. So decision logic will decide based on the syndrome. If all bits are 0 in the syndrome, then decision logic will accept the data word part in the code word and it is sent to the upper layer, that is network layer. Okay, that means the received code word has no error, or received code word has error, or it is not detected by the receiver, or receiver is unable to detect that error. So two possibilities are there. Okay. Now the second case, assume that the code word is received with error, that is one or more bits of the code word received has error or it is corrupted. Now the checker will perform the division operation for the received code word, and if the syndrome is a non-zero value, if some bits or any one of the bit in the syndrome is not 0, it is 1, then decision logic will simply discard the received code word and it will ask the sender to resend that frame again. Okay, so this is called retransmission. So here error correction is not possible because we don't know the which part has error or which bit has error. So detection is not possible. Therefore, the correction is also not possible. So simply the detection is possible, only the location of the error is not possible. Here. Now let us take an example. The encoder. What happens in the encoder? Let us take an example here. Let n, what is n? The number of bits in the code word. It is 8. K equal to 5. That is number of bits in the data word. So if you form n minus k, we have 3 here. So 3 zeros to be appended. This is one way of finding the number of zeros to be appended. Or in other words, here we are using a 4-bit divisor. 4-bit divisor. So therefore, the number of zeros to be appended for the data word is 3. Here you see we form an augmented data word by appending 3 zeros to the data word. So we get 5 plus 3 total 8 bits. 8 bits in this augmented data word. And divisor which is used here is 1011. Okay. Now perform the modulo 2 division here. So as I mentioned earlier in my discussion, modulo 2 subtraction. Here basically we perform subtraction. So modulo 2 subtraction is same as the XOR operation. So therefore, here one more point you have to remember: if leftmost bit is 1, leftmost bit is 1. Okay, leftmost bit is 1, then that is leftmost bit. This is 1. So you have to take 1011 1011 as a divisor, and we perform the XOR operation. So 1 plus 1 is 0. We have to simply discard that 0. We don't need, because at the end we need 4 bits. We take this 1 here. So therefore total 4 bits. Simply ignore this. So 0 XOR 0 is 0. 0 XOR 1 is 1. 1 XOR 1 is 0. So this 1 is taken here. Now again, leftmost bit is 0 here. Leftmost bit is 0. So therefore you have to take 0, 0, 0, 0 as divisor. So you take 0, 0, 0 as divisor and perform XOR operation. So 1 XOR 0 is 1. 0 XOR 0 is 0. 1 XOR 0, it is 1. And this 0 is taken here. Now again, leftmost bit is 1. So therefore 1011 is taken as divisor. So again perform XOR operation. 0 XOR 0 is 0. 1 XOR 1 is 0. 0 XOR 1 is 1. And this 0 is taken. Since leftmost bit is again 0, you have to take 0, 0, 0 as a divisor. So here 0, 0, 0 as a divisor. 0 XOR 0 is 0. 1 XOR 0 is 1. 0 XOR 0, it is 0. And this 0 is taken here. Okay. Now at the end, we get, see, 0, 0, 0, 0 is taken as a divisor because the leftmost bit is 0 here. Okay. So perform XOR operation. 1 XOR 0 is 1. 0 XOR 0 it is 0. 0 XOR 0 is 0. So we got 1, 0, 0 as a remainder. Remember, there are 3 bits in my remember, that is equal to the number of bits which are appended, number of zeros which are appended to form the augmented data word. So that is 3 here. So the code word sent, as I mentioned in my previous diagram, code word sent will have 2 parts. The data word part, the higher part is the data word part, and the lower part is the remainder. So remainder is appended to the data word to form the code word, n bit code word. So here n is 8. Now here, so the decoder at the receiver side does the same division process as the encoder. And here the remainder of the division is called as syndrome. We use a term called syndrome here. Now, as I mentioned earlier, at the receiver side, there are 2 cases. The first case is code word received without error. Code word received without error. That means the received code word is this one, same thing, which is same as the sent code word. Okay, so no error here as it is received. So the decoder will perform the division operation for the received code word using the same divisor which is used at the sender side. In our example, at the sender side we have used 1011 as a divisor. So therefore we have used 1011 as a divisor at the receiver side also. Now here, since the same division modulo 2 division operation is performed here, if the leftmost bit is 1, you have to take 1011 as a divisor. Here this 1 is taken here. The leftmost bit is 0, 0, 0, 0, 0 as taken as a divisor. And division operation continues here. At the end we got remainder. So that is called a syndrome here. All bits are 0 here. All bits are 0. As I mentioned earlier, if all bits are 0 in syndrome, that means received code word has no error. It is not corrupted, or it is received without any error. So, and here one more thing, in the division operation, we have to simply discard the quotient. Quotient is not used. So we are interested only in the remainder. And case 2, case 2 in the encoder is received code word has error. So code word received with error, that is one bit is corrupted here. This bit is error bit here, that is the fourth bit from the right, or it's also called as fourth LSB. It is corrupted. That means it is sent bit is 1, the received bit is 0. Now the receiver will perform the same division operation for the received code word here. Again you see, if the leftmost bit is 1, 1011 is taken as a divisor. If leftmost bit is 0, 0000 is taken as a divisor. So this division process continues here. It continues. At the end we got 011 as syndrome. 011 as a syndrome. You see here there are two bits S0 and S1. There are two bits are not zeros. We got a non-zero syndrome. If any one of the bit is a non-zero, then the decoder in the checker in the decoder will simply discard the received code word. That means received code word has error. In this example, it is single bit error. Okay, single bit error. So finally, the conclusion is this: if syndrome not equal to 0, one or more bits are corrupted. One bit is corrupted or more bits are corrupted. In our example, we have taken only one bit. It will be one bit or more than one bit also. It can be a burst error also, already detected. Our second case, that is the case number 1, what we discussed in our example. If syndrome equal to 0, either no bit is corrupted. Okay, that possibility is there. Either no bit is corrupted, or some bits are corrupted, but the receiver has failed to detect them. That possibility is also there. Okay. So in this case, the location of the bit, the corrupted bit is not identified. Okay. Simply the receiver will ask the sender to resend the frame. This is about this. And here some of the advantages, it's very easy to implement using a hardware that we'll discuss later in the next session. And it is very simple, and it can detect one error, two error, more than one error. It can also detect a burst error. Burst error means a group of errors. Okay. So it's a good technique which is widely used in data communication technique. Now, this CRC codes are also called as, another name is called as polynomial codes. Polynomial codes. What is polynomial code? CRC is also called as polynomial code. A pattern of zeros and ones can be represented as polynomial with coefficients of 0 and 1. Here, remember, in ordinary polynomial arithmetic, the coefficients will be a real value. Okay, we have 1.1, 1.21 like that. But here, the coefficients are zeros and ones because we are simply representing the binary patterns. Okay. Then power of each term shows the position of the bit. Power of each term. For example, here x power 0, that is position 0. X power 1, position 1, like that. X power 6, position 6. You see in this example, you have a bit pattern 1, 0, 0, 0, 0, 1, 1. So 1 is a coefficient multiplied by x into 6. What is this 6? 6 is a position of the bit. Similarly, 0 multiplied by x power 5, 0 multiplied by x power 4, 0 multiplied by x power 3, 0 multiplied by x power 2, here 1 multiplied by x power 1, 1 multiplied by x power 0. And simply, because these three terms, these three terms here, these three terms are zeros, so we can simply neglect that, and simplified version is x power 6 plus x power 1 plus 1, because x power 0 is 1. That is the short form. Then how do you represent that? The degree of polynomial is the highest power in the polynomial. So in this example, degree of polynomial is 6 because the highest power is 6. Or in other words, the degree of polynomial is 1 less than the number of bits in the pattern. 1 less than the number of bits in the pattern, because there are 7 bits in our example. So degree of polynomial is 1 less than the number of bits. Now we perform some arithmetic here, because we require that when you perform the modulo 2, the division, adding and subtracting. See, adding and subtracting polynomial are, how do you do in the mathematics? It is simply adding or subtracting the coefficients of terms with same power. Okay, for example, x power 2 plus x power 2. We get 2 into x power 2, right? So here, in our case, the coefficients are only zeros and ones. The adding is in a modulo 2. That is 1 plus 1 equal to 0. Okay. So now there are two cases here. The addition and subtraction are the same here. Addition and subtraction are the same, because basically we perform modulo 2 addition and modulo 2 subtraction. In modulo 2, addition and subtraction are the same. Or adding or subtracting is done by combining the terms and deleting a pair of identical terms. That means here, you see here, so adding these two, we get x power 6. Here x power 4 plus x power 2, there is a pair of x power 4. You simply delete that. Why you delete? Because it is, when you perform modulo 2 addition, it will be 1 plus 1. So in modulo 2 addition, 1 plus 1 equal to 0. So therefore we simply delete this. So at the end we get x power 6 plus x power 5. Then x power 4, there are two terms, they are deleted. X power 2 plus x power 2, they are also deleted. Okay. And if there are, assume that if there are 3 terms, x power 2, 3 times, then you have to delete only the pair. Pair of them should be deleted and keep the third one. That is 1 plus 1 plus 1. So what do we get? 1 plus 1 is 0, 0 plus 1 is 1. So you have to retain 1 there. And multiplying, again same, simply adding the powers. Dividing is simply subtracting the power. Okay, that's similar to the ordinary multiplying. It is, you can see the example here, multiplying these two, x power 7 you get x power 2 multiplied by x power 5, and you get here, this is what is this, and here x power 5 is there in here, is a pair, as a pair, it is deleted. Similarly, x power 4 also is there in 2 places, it is deleted. X power 3 is there in 3 places, so one pair is deleted, retaining the third one, that is this one, and you have x. So this is an example for multiplying. And shifting. A binary pattern is often shifted a number of bits to the right or left, we can shift. You can see this example. 10011 becomes 1000. 3 bits are shifted here. Okay, left shift 3 positions. So before shifting, we have the polynomial representation of this pattern. See, polynomial representation of this pattern is this. Okay, now the polynomial representation of this one is this. Okay, we get x power 7 here, the highest power, because 3 bits shifted left. How do you got this? Simply you add that 3 to this, the power. So 4 plus 3 is 7. Here 1 plus 3 is 4. Here it is x power 0. So 0 plus 3 is 3. So we get. Similarly, the next one, shifting right. Okay. So now let's take an example. Okay. Now this example shows how to generate a code word at the sender side using polynomial division. So find the code word at the sender side using CRC polynomial division. The given data word is this. So given data word is this. So given data word is this. Okay. This is a divisor. Generator polynomial means it's a divisor. So we represent the data word as d of x. So this is your d of x here. This is your d of x. D of x. And you represent that using the polynomial representation. You see there are 9 bits, so highest power will be x power 8. So 1 into x power 8, 0 into x power 7, again 1 into x power 6, 0 into x power 5, 0 into x power 4, plus 1 into x power 3, 1 into x power 2, plus 1 into x power 1, plus 1 into x power 0. So after simplifying, we get this. And we form the augmented data word. As we mentioned earlier, how do you form the augmented data word? You have a data word, and how many zeros to be appended here? 4 zeros. Why 4 zeros? Because there are 5 bits in the generator here. So therefore 1 less than that. So 4 zeros to be appended. So we get the augmented data word. Now here you see this. We have simply shifted. Appending 4 zeros means shifting 4 bit left. Shifting 4 bit left. So therefore, we have to add 4 to the each power. So 8 plus 4 is 12. We get 12 here. 6 plus 4 is 10. 3 plus 4 is 7. Like that. The last term is 0 plus 4 is 4. Similarly, the generator polynomial which is given, that is the divisor, 10111, and its polynomial representation is this: x power 4 plus x power 2 plus x power 1 plus x power 0. Now let us see how to perform the division operation. This is a generator polynomial or a divisor, and we get augmented data word. This we have already got augmented data word here. Augmented data word. Okay, here you see here x power 12, x power 12 is their highest power, and here you have to take, you have to see this, see how you take when you multiply these two, x power 4 and x power 8. You have to choose this term in such a way that after multiplying this and this, okay, multiplying means adding the powers. So you have to get this one, this term. That means here you have to take x power 8. If I add x power 8 here, x power 8 multiplied by x power 4, it is x power 12 we get. Then x power 8 multiplied by x power 2, we get x power 10. X power 11 is not there, you have to take it as 0 here. Similarly, x power 5 multiplied by x power 1, we get, x power 8, x power 8 multiplied by x power 1, we get x power 8 multiplied by x power 4, I'll repeat this, x power 12, x power 8 multiplied by x power 2, it is x power 10, then we get x power, this one, x power 10, and x power 8 multiplied by x power 1, we get this x power 9 here, then x power 8 multiplied by x power 0, we get x power 8 here. Okay, then see here you have to perform modulo 2, it's a subtraction. Subtraction means basically you are adding the two terms. Adding the two terms means adding the identical terms means deleting them. So this is deleted, here this is deleted. Now 0 minus x power 9. It is same as 0 plus x power 9. So that is x power 9. Here 0 plus x power 9 is x power 8 because addition and subtraction is same here. Then here for this again Here you take this one x power 9. X power 9, here take this x power 9. So x power 9 is there here. You have to take this term in such a way that after multiplying with this, you have to get 9. So you have to take x power 5 here, so that x power 5 multiplied by x power 4, we get x power 9 here. Okay, then x power 5 multiplied by x power 2, it is x power 7. So x power 8 is not there, so therefore it is 0. X power 5 multiplied by x power 1 is this x power 6. X power 5 multiplied by x power 0, that is x power 5. Now you perform this thing, x power 8, this is 0, x power 8 plus 0 is x power 8, then x power 7, x power 6, x power 5. Remember, you are performing addition here. So addition and subtraction are same here. Okay. Then since x power 8 is there here, x power 8 is there here, x power 8 is there here, x power 8 is there. So what you have to take to get x power 8? You have to get x power 4 here. So here we have x power 4 plus x power 4, we get x power 8. Then x power 4 multiplied by x power 2, we get x power 6 here. Then x power 5, x power 4. It continues like that. At the end, we get the remainder. At the end, we get the remainder. You see here x power 2 plus x. So that is our remainder. We represent that using r of x. R of x. So your r of x is x power 2 plus x. So the code word sent here is, first you take the data word part. Not the augmented data word, it's simply the data word plus the remainder part. So this one, your data word, that is this, here this one, plus the remainder. That will give you the code word sent. So this is a polynomial and its binary representation is this. So this is a code word sent. So this is polynomial arithmetic. It's very easy to identify and very easy to perform here operation. So therefore this is normally used. Thank you.